Good morning, everyone, and thank you for your attendance with us today. Welcome to our webinar towards the implementation of the EU Green Deal to the production of sustainable fuels and chemicals that have been organized in the partner event EU Green Week of 2022, as you all know. In the next slide, you will see my name. Thank you. My name is Maria Navarro. I work at UECAD as a project coordinator, and I will give you a brief overview of what is this Road to Green Chem cluster that has organized this one. So, talking about the cluster, what is Road to Green Chem? We are 6 European-funded projects whose logos you can see on the screen. We are SunCoChem, Recoder, Photoelectrochemical, Solar2Chem, Decade, and Ocean. We are all developing and demonstrating innovative technologies with the ultimate goal of eliminating the use of carbon feedstock in the chemical industry. All project addresses growing needs for, which is also aligned with the European, the EU Green Deal goals. Growing need for secure, clean, and efficient energy, more efficiency, the use of resources in an efficient way, sustainable raw materials, clean and green production of chemicals without fossil fuels, and also the use of safe and sustainable by design new chemicals and materials. I will explain you now our mission of the Road to Green Chem cluster in the next slide. Yes, so our mission, first of all, is engagement with academia, industry, and policy stakeholders to showcase the advantages of a solar-driven chemical industry in Europe, in order to move fossil fuel-based industry to a greener industry. Highlight the green production of chemical products and drive a move away from fossil fuels and chemicals manufacturing, as I was telling before, to green chemicals manufacturing. And the development of demonstration of innovative technologies in real-world settings in order to support a wider uptake of these technologies, especially by the industry, but not only by the industry. Okay, so in this slide, we are seeing an overview of the agenda today. As you see, our agenda is quite tight because we have a lot of presenters. The webinar is divided into 3 sessions. The first session is dedicated to the development of sustainable solutions for a greener chemistry sector. The second session will talk about the demonstration of the real impacts of electrocatalytic conversion solutions for a sustainable chemistry industry. And the third session, so our presenters will talk about upskilling future chemical technicians and researchers to implement green chemical goods. All right, we will leave some time right after the end of our chemical around 12 o'clock for questions and answers. So if you have questions for our presenters, please write them in our chat. Don't forget to include also the name of the presenter that the question is addressed to. Okay, so the different presenters know exactly which question they should answer. We will have the exception here of our next presenter, Ana Chloe de Vic, who unfortunately she had other commitment and cannot stay until the end. So the questions for Ana Chloe will be addressed right after her presentation. Okay, please take that into account. Now I will present Ana Chloe briefly and then give her the floor. Ana Chloe de Vic, interim EPP Secretary and National Technology Platforms Coordinator in SunCoChem. She has a master's degree in chemistry and chemical engineering, specialized in polymers from the École Nationale Supérieure de Chimie in Montpellier, France. She is Senior Innovation Manager in the European Chemical Industry Council, responsible for innovation policies and funding opportunities. She is currently coordinating the area of advanced materials and 17 SunChem's national technology platforms for the European Platform Sustainable Chemistry. This is SunChem. So, Ana Chloe.
Good morning, everyone. So I'm pleased to give you a bit of overview. I understand from your agenda today. So it's really trying to to understand how the chemical industry and all its stakeholders, policy stakeholders, academy, and so on, how we are working together to develop chemical innovations and how we are getting to the EU Green Deal agenda. And for this, we have the SunCoChem platform. So I don't know how many of you know about the SunCoChem technology platform. So I will introduce very briefly this platform. So next, please. So this platform exists actually for like more than 15 years. So it's the European Technology Platform for Sustainable Chemistry. We are trying to bring together industry, academia, and policy groups, as well as the wider society. One unique feature of this platform is that we have 17 national technology platforms. That's quite enriching, actually. So we have a coordination of all the different national networks. So we have many countries. There you can see below on the slide the founding members. So CEFIC, the trade association for the chemical industry, is a founding member, and we also operate the platform together with other stakeholders. Then you have the German Society of Chemistry, also the British Society of Chemistry, and an important feature for SunCoChem is the biotechnology. We want to unify the sustainable chemistry with biotechnology, and that's why we have Europa Bio also as a founding member and member of the SunCoChem board. Next, please. So really, this is what I just mentioned. The vision is really working for a competitive and innovative Europe, and where the sustainable chemistry and biotechnology together provide solution for the future. That's our main vision and driver. What we want to do is really develop R&I funding schemes. So we want to work hand in hand with the European Commission and with all the different funding programs, Horizon Europe, but not only, anything which is needed for the chemical innovations, and also looking at the innovation capacity of Europe, of our industry, how we can going further in investing in low carbon energy and circular economy and other topics that I will develop further. Next, please. So that I will not go into detail, but you can get the the slides. So all what we are doing you're welcome, if you don't know the platform, to apply. So you go to the site suncochem.org. It's completely free of charge. So it's a very open platform. So that's it for SunCoChem. Next, please. So yeah, this is the heart of our activities, partnering with the European Commission and trying to give input on topics for the calls. In the past, so we have been working quite closely with SPIRE, like now it's called Processes for Planet, P4P. In the past, we were working with the NMBP program for Horizon 2020, and for Horizon Europe now it's the prosperity direction of the GRTD, and more specifically the unit industrial transformation, the unit E3 of the GRTD that we are collaborating a lot with, because they are involved with chemicals and materials, and also the P4P, like all the processes part. And our guidance for now, but we are just like fastly moving in other agendas, but it's still very valid. It was published at the end of 2019. it's a strategic innovation and research agenda of SunCoChem, so that you can have access in the publications page of the SunCoChem website. So next, please. So yes, the green, how we link with the Green Deal. Basically, we link everywhere. You know, the chemical industry is everywhere in all of the different value chains. So potentially we have solutions for all the different challenges that are exposed in the Green Deal, like the renewable energy, the clean road transport, circular economy, public health, electronics like the CHIPS Act, and also aerospace. So chemical industries is everywhere. That's why we say we represent the industry of industries. And that's one of the challenges that we have today, especially to try to get much more closer to our downstream users. Next, please. So this just to show you how all the different objectives of the Green Deal are impacting the chemical industry. Here it's at EU level, but we are all there. You know, the climate law, the energy efficiency directive revision, the more recent sustainable carbon cycle, where we have the objective of CO2 removal. Then we have also pollution, air pollution, biodiversity. Now, in the circularity agenda, we have also the objectives of the recycled content target for all the polymers that we produce. All the legislation on waste, we are involved too. Packaging, the revision of the Waste Framework Directive. So you can see that there are like many. Next, please. So this was on the EU level. Now, if we deep dive a little bit more at our sector level, like the chemical industry level, you can see that, for example, on the sustainable carbon cycle, that would get maybe more interest from you, that we are with an objective of at least 20% of carbon used in the chemical and plastic products, which should be from sustainable non-fossil sources by 2030, which is a huge challenge. Then on the renewable energy directive, we also have a big objective of implementation of renewable energy. Now and that's more specific to the chemical industry. Now we have this new chemical strategy for sustainability, which has a lot of different objectives, and this is for positive impact on the environment and health. I'm going to detail this a little bit more. Production and use of safe and sustainable by design chemicals through their life cycle. So that's like a big topic today on our agenda at SunCoChem. Ban most harmful substances. You know that they are like a revision of REACH and CLP, and we also have to work on the PFAS, which are the fluorinated compounds that we are going to be banned. And then on the circularity part, we have to work on the non-toxic material cycles. So next, please. So another one is the digital objectives. You will have heard again about the digital product passport. So that's a new legislative package which is called Sustainable Product Initiative. It's sustainable. It's a new law. It will be over several years, but categories of products will have to go through a number of requirements. An example that you can use today is this new regulation on batteries, the Sustainable Batteries Regulation, which is now under trialogue. So it's like well advanced. So it will be one of the first legislations showing how we can develop sustainable products. So the batteries of the future will have to have a digital passport, will have to have carbon footprint requirements, recycled content requirements. So this is just a teaser for all the different other products which will come afterwards, where we will have to have all these requirements. And digital objectives, very, very important. Chemical production, but of course all other industries will enable actually to reach the Green Deal objectives. So that's part of our innovation agenda also. Next, please. So just a zoom on this, because yeah, it concerns specifically the chemical industry, and then also the full value chains where all chemicals and materials are getting into. So it's just like this new aspect that where you have an interplay of regulatory measures and innovation support, like where innovation is desperately needed if we are going to improve the protection of health and environment. We have to develop safe and sustainable chemicals. So we have to start with a design phase. And so this can be done by reforming REACH, but that's not enough. We have to go much further. We have to develop products which are safe and sustainable by design. So this is a big agenda at the moment. SunCoChem and obviously other stakeholders are collaborating with the Commission to develop, propose criteria how we can design products which are safe and sustainable. Next, please. So this is it. This safe and sustainable by design approach is new in a way that you are grouping the safety aspects of the products, and that you make sure that there is no harmful substances from the beginning in your design, in the design of a product, but not only a product, obviously of a process. And I'm talking to you also when you're developing in your projects, your processes. The safety part will now have to be completely integrated, not only for the final product that you are aiming for, but also during the production phase, during the processes. And then all the sustainability that we know, which is the full life cycle for a product. So it's really looking at the life cycle analysis, but now including also the end of life, finding a solution for end of life. So we don't want to have any toxic materials if a product is going to be recycled. We want to have a solution for all end of life products. And what do we need for this? We need an assessment framework. So it's like an innovation process, right? So we are at CEFIC. So basically at CEFIC on the business side, we have this stage gate process which is being used. What we have been working on is what is called the PSA methodology, portfolio sustainability assessment, and this has been taken up on board by many corporates, many big companies. So yeah, it's progressing, I would say, on the corporate level. So it's the WBCSD organization, which has got more than 100 corporates, and it's a global organization. So they are working actively on improving these innovation processes. But maybe one of the biggest challenges that we will have in the next years is how we get all this implemented in a simple manner, because we don't want to bring complicated processes. how we will implement this in SMEs, in small companies. So that's very important to mention, and that will be the subject also of Project Future Horizon Europe project. One is going to be started very soon. It's a CSA project, which is about building a community on safe and sustainable by design approach, and how we can enable the implementation in precisely in SMEs, and also all the education networks, universities, but not only, like schools and everything. Next, please. So yeah, here is just so that you see, and that's still to be defined, which criteria are going to be chosen for this innovation process. How far do we go? The SHE profile being obviously first in the list, but then yeah, circularity. You have many criteria which can be chosen. So it's a complex process, and that's why it's going to take time. But hopefully, we will end up with a simple enough process that everybody can get on board and apply this process. And beside the environmental criteria, obviously we have the market-related criteria, because the product performance should be first on the list. If you don't have the product performance, of course, you cannot have the other criteria. It doesn't serve. You look first for a functionality, and then social criteria also very important. The employment, the impact of an innovation is how much employment this can give, so that you know from the different European projects where you have to evaluate the impact on employment, and so on and so on. So that's really work ongoing at the moment. Next, please. This is just to inform you that beside this safe and sustainable by design approach and criteria which are going to be proposed by the Commission. So we are many stakeholders working together, and the Commission is going to publish a document in October on safe and sustainable by design, but they also are working on a strategic research and innovation plan, which is linked with the chemical strategy for sustainability. And what is pretended to do here is to have a holistic approach, is working across sectors and addressing the interdependencies of the EU strategies. So it's really connecting the dots between all the different EU Green Deal objectives. The toxic-free environment and circularity, as I mentioned before, improving the safety aspects along the life cycle of chemicals, materials, and products, and also working on durability, go towards durable products, not forgetting the resource efficiency, reuse and reduce waste streams, and recycle to recover energy, chemicals and materials. So you can see that everything is covered basically. So this document that they are going to publish in October is going to be still on a high level, right? But it will cover more or less the overall agenda that we have to work on in the next few years. Next, please. So here is these are slides from the European Commission. So it's just to show you that this process has started end of last year, end of 21. So it's really developing this overarching plan, as I mentioned, and with the objective to make the Green Deal compliant, to make all the different aspects Green Deal compliant. So basically, it's really building together between different stakeholders the key research and innovation needs, and that we will be able also to give some guidelines for the funders, the not only the European Commission, but all the different institutions who can help in giving funding, basically, on research and innovation, like national fundings, European Bank, and so on and so on. Next, please. So this is just the first idea. We don't know yet. We don't have the draft or anything, but more or less this is what it's going to look like. This research and innovation plan. So you have the first block, which is about sustainable processes and technologies. So you have sustainable sourcing, secondary raw materials, green and efficient production processes, and the business models. Now you have a block on safe and sustainable by design chemicals and materials, as I have mentioned before. Here you can see safe and sustainable by design toolbox. And I mentioned digital. I think digital here is going to be very important to be able to do simulations and to be able to do your innovations. You will have to have a toolbox to be able to do iterations, right? Like the eco-design methodology, but in a more efficient manner. Next, please. So here you have the safety part because this is part of the chemical strategy for sustainability. So there will be a block on exposure, how we can improve like the monitorings, the models, methods, the hazard part, and the risk assessment part. So that's also a research and innovation need to anticipate much better the problematic substances. Next, please. And at the end, there will be a block on decontamination and remediating pollution, and then fair data. So how we can have open access. Everyone can have access to data without compromising the confidential business information always required by the different businesses. Next, please. So this is it. What we are now looking at is providing sustainable solutions, and we are busy like developing technology priorities and the research and innovation actions which are necessary to develop those sustainable solutions. So we have different blocks. We have the materials, advanced processes. We have formulations and actives. We put this because it goes a bit more downstream. Like you have the, for example, detergents applications from in the materials, also developments. Here in the formulations, it's more like the small companies, precisely how they can develop formulations which are safe and sustainable by design. And actives it's going together with the formulations which are like the active ingredients of a formulation, and the enabling digital technologies, which is also key. And I put here there through value chains collaborations, maybe that we have not done enough until now, and that we will do definitely. So we will have to build research and innovation agendas, roadmaps per value chain, basically, and connecting between the chemical industry and all the downstream users. Next, please. So here is just like you can see this in the CIRA that I showed you just at the beginning, so that you see all the different aspects that I have already mentioned. Here you can have this graphic on advanced materials, which shows solutions for every step of the value chains. And the design phase you can see already. So this is coming from 2019, but you can already see here that in the design phase, we were considering the design for circularity, safe by design, sustainability assessment. And then in the advanced materials, you have all the different functionalities that we are looking for. And we have also the industrial value chains. It's not only about downstream user, it's about developing materials for energy. So that's just an example of all the different solutions that we are working on. Next, please, so that you might get more interested in advanced processes. So here I have the image of a reactor, and so you have all the different processes to be developed: electrocatalysis, power to chemical, industrial biotechnology, waste valorization processes, also design of new reactors. You have obviously all the separation technologies for the waste to make quality waste so that they can be properly recycled in existing reactors, I would say, or that you don't have to build a completely new plant. CO2, as you well know, you have to develop all the different separation technologies. Hydrogen, a very important vector that also is a big technology topic. And water also is a big topic for developing waste treatment efficient technologies. Next, please. So here, this is an infographic from CEFIC, which I thought it was interesting to show. So this is just like showing the CO2, the carbon, sustainable carbon cycle, and the different sources for carbon, from biomass, CO2 to waste, domestic waste, plastic waste. So you have your chemical production, which are C-based always, even if they are CO2 based, it's always carbon based. Then the chemical use, and then you have the chemical recycling for treating the waste, so that can go into the plants. Then you have the bio-based chemistry also, and all the different capture and purification processes. Next, please. And this is just an infographic just to show how digital transformation is impacting our industry and many industries. So this is showing everywhere in a company where digital has a role to play. So the cognitive plants, the laboratory, like in the chemical area, you have like computational chemistry. We are going to design materials through machine learning and artificial intelligence driven research, process analytics, even risk management, industrial symbiosis with the other plants beside, and as also mentioned before, supply chain integration, like we will have to trace all the information through the supply chains. And I think that's my last example, and I hope I have given a good overview of what is at stake here for chemicals and the chemical industry.
Yes, indeed,
Thank you. Thank
it
you.
was a very exhaustive presentation. Okay, so there are no questions for Anne. In which case, we are going to jump to our next presenter, Miriam Díaz de los Bernardos. Okay? Miriam holds a degree in chemistry and a master's degree in synthesis and catalysis, and she obtained a PhD in organic synthesis in 2012 from the Universidad Rovira y Virgili of Tarragona. Currently, she is the head of the synthesis and catalysis line at the Chemical Technological Unit in EURECAT. She is the scientific coordinator of the EU-funded project SunCoChem. Her expertise covers organic synthesis and the design of ultra-selective new catalysts to obtain industrial relevance products from waste feedstocks such as CO2 in thermal, photo, and electrochemical processes. Miriam, the floor is all yours.
Okay, so good morning to everyone. I would like to briefly explain which are the main technical approaches that we are exploring within SunCoChem project towards the development of a photoelectrocatalytic reactor for the production of oxo products, starting from CO2, water, and solar energy. Around 90% of the chemicals are based on fossil fuels. In fact, in Europe, the chemical industry is the third largest greenhouse emitter with over 30 gigatons of CO2 emitted per year. So there is an urgent need towards the development of new emission-free processes. In this context, the electrochemical conversion of CO2 towards the production of chemical feedstock and fuels offers a way to turn waste emissions from the industry into valuable products. And this technology, when it's coupled with renewable electricity, allow to obtain those valuable products with a net negative carbon footprint. However, if we compare all the products that we can obtain by the electrochemical reduction of CO2 in terms of technical parameters such as Faraday efficiency and the current density, it seems that the short chain molecules currently present the most economically targets for short-term implementation. In fact, carbon monoxide is one of the more important building blocks for the chemical industry. Is used to introduce carbon functionalities in a large amount of chemical processes such as Fischer-Tropsch, formulation reaction, carbonizations, etc. So we believe that integrated electrochemical reduction of CO2 into carbon monoxide with its follow-up utilization with thermocatalytic process to produce oxo products can slowly electrify the oxochemicals sector. Well, in this context, the SunCoChem concept is based on the development of photoelectrocatalytic device. This device will be fed with water and CO2 direct from the flue gas of the company Dow Iberica here in Tarragona, and will be driven by energy of the sun. So we are electrochemical produced carbon monoxide as a chemical precursor for in situ in the same device, coupled with a tandem hydroformylation process to produce different oxo products. Those three oxo product targets. So we plan to manufacture from CO2 and water those three oxo products. For instance, glycolic acid will be produced from the hydroformylation of formaldehyde, and balealdehyde will be produced from the hydroformylation of butene. Here, I would like to point out that butene also is going to be delivered from Dow. Dow here in Tarragona has a plant of the steam cracking reforming of naphtha to produce ethylene, and they obtain butene as a waste byproduct. So we are going to valorize Dow butene and Dow CO2 to produce balealdehyde, which actually is also produced and manufactured in Dow. And Dow is, of course, joining the project. And also limoxal, it's going to be produced by the formulation of limonene. This product is actually produced in IFF in Benicarló, and IFF is also joining the consortium of the project. So here I just want to briefly explain which components integrate a PEC system for the CO2 reduction and how it works. So the main system are the photoabsorber and a CO2 reduction catalyst and an oxygen evolution reaction catalyst. The photoabsorber captures light and produce electrons and holes. The electrons are transferred to the surface of the CO2 reduction catalyst to reduce CO2 to the corresponding fuel, and then the holes are transferred to the oxygen reaction catalyst to oxidize water and produce oxygen. The ionic transport is also very important to obtain a good efficiency. Every time that the electron arrives at the cathode, we need the corresponding ionic movement to maintain the neutrality of the overall system. So here is the current record of the solar-driven CO2 conversion to carbon monoxide with solar to fuel efficiency around 40% using a PEC device. Here, as you can see, that the operation point of the system is determined by the power curve, which is mainly given by the photoabsorbent component, and the loading curve which is mainly given by the electrochemical process. In this loading curve, there are different components that are included. For instance, we have the thermodynamic voltage window, which is in fact the minimum energy that we need for the reaction to occur. Here is the thermodynamic voltage required for the CO2 reaction to CO2. Also, we have voltage losses for the kinetic overpotential for both catalysts. That is determined by how good are your catalysts. And also potential losses determined by the difference in the concentration between the reactions and products, and also the ionic transport losses. Those two losses are mainly generated by the architecture of the device. So if we want to produce carbon monoxide from CO2 at this current density, we at least have to develop a device that will give us a current voltage of 2 volts. And which are the objectives that we are planning to obtain with our device? We want to manufacture a device with an overall sunlight to carbon monoxide conversion efficiency superior to 10%, and that will give us a solar current density for cogeneration of 20 milliampere per square centimeters. We want to manufacture a device that will lose less than 5% of its performance under 1,000 hours of operation, and that will decrease more than 50% the CO2 emissions in comparison with actual technology routes for the production of auto products from fossil fuels. So how SunCoChem sorry, are you seeing my slide? I don't see my slide anymore.
No, we are seeing the first slide, and not in full mode.
Now?
Yes. No.
Okay. Sorry. So how SunCoChem is addressing those challenges in terms of material development to obtain those target objectives. So in terms of photoelectric development, the photoelectrodes, let's say it's like the core engine of the process, because it provides you the sufficient current and voltage for the reaction to take place. And in the literature, you can photoelectrochemically reduce CO2 to CO quite well in both homogeneous and heterogeneous systems. For instance, rhenium catalyst when it's combined with p-type semiconductors based on silicon can decrease the photovoltage generated for CO2 reduction to CO, showing a good turnover frequencies of the catalyst. And in the other hand, the voltage of the cell will be limited by the band gap of the semiconductor that we use. So a single junction of photoabsorbent will not provide you the sufficient voltage for the reaction to take place. So here what we are doing is trying to combine different photoabsorbent materials to obtain the required voltage that we need for the device. So the photoelectric development in SunCoChem are based in a multi-heterojunction for Z-shim mimicking in both the anode and the cathode, based on metal oxide semiconductor nanoparticles, molecular organometallic chromatophores as photoabsorbers, and also molecular organometallic catalysts for water splitting, water oxidation reaction, water CO2 reduction reaction, and hydroformylation reaction. Concerning the ionic transports, as I said, we need a very efficient ionic transport. And here we can take a lot of inspiration from PEC device for water splitting, where it's necessary to work in 2 different pH conditions. So in SunCoChem, we are developing transparent bipolar membranes where they can provide protons to the cathodic part for reduced CO2 and OH minus species to the anionic part to the anodic part to oxidize water, and those species are generated by the dissociation of water in the interface of the membrane. And something also very important to obtain a device with a very good efficiency is how robust your device delivers the CO2 into the electrode surface. That's why here we are using, instead of aqueous electrolytes, we are using imidazoline-based ionic liquids electrolytes. As you can see, using these electrolytes, we can increase the CO2 solubility in comparison of water electrolytes up to 30 times or less. And those ionic liquids have very good properties for this kind of technologies. They have better physical absorption, lower viscosity, higher CO2 and organic reagent solubility, and a higher electrochemical stability. And they also can interact, imidazoline green can also interact with the CO2 radical anionic species that is necessary for producing CO, decreasing the lower potential of the reaction and the over potential of the all processes. So in the end, they also act as a kind of co-catalyst of the system. So in the end, we are going to integrate all those materials in a device that will integrate 3 different chambers in a single unit. An anodic chamber for water oxidation, cathodic chamber for photo-assisted CO2 reduction to CO, and tandem thermocatalytic ion formulation to oxo products, and a flue gas CO2 capture chamber where directly the flue gas from Dow it's gonna fit into this chamber to selectively capture CO2 with asymmetric pollution for membranes and ionic liquids. So the SunCoChem project is investigating 4 major actions, and there are 7 work packages in a 4 years period. And the first phase is development of materials and components of the cell, and we are actually finishing that phase. Then upscaling, testing, and validation of the device at TRL3, and we are starting this part actually. Then the integration and optimization of the manufacture of the final prototype device. Here we are going to develop a validation of 1 square meter device in the facilities of IFF company in Benicaló for the production of the oxo products. And also we have a non-technical part that evaluates how our technology will impact in terms of environmental, socioeconomic, the actual technologies of this oxo product generation and also dissemination activities. So that's all. That's our team. It's constituted by 14 partners from 8 European countries. The project is coordinated by ERICAT, in concrete from the Unit of Chemical Technologies in Tarragona. The scientific coordination is shared with Professor Hernandez from the Politecnico di Torino in Italy. And I really have to acknowledge all the partners that are joining the consortium for the super good job. And this is a very collaborative project because we are always sharing components between one institution into another, and sometimes it's complicated, but I have to say that here it is not, so I'm very grateful for that. So that's all. Thank you all for your kind attention.
Thank you very much, Miriam, to you for this nice presentation. So now we are going to jump to our next presenter, who is Dr. Pau Ferrar. Okay? Pau is a lecturer in chemistry at the National University of Ireland, Galway, in September 2005. He received his bachelor degree in chemical engineering from the Autonomous University of Barcelona and obtained a PhD in chemistry from the Material Science Institute of Barcelona in 2009. He's the director of the ChemLight group. This group is focused on the preparation of molecules and materials capable to drive light-driven reactions to the production of fuels and chemicals. So, Pau, the floor is all yours now.
Thank you, Maria, for the kind introduction. So it's a pleasure for me to talk about the Flow PhotoChem project that, similarly to the colleagues in SunCoChem and Decade, we started about 2 years ago. So Flow PhotoChem is about integrating reactors for the production of green ethylene. So what's the project background. So as Marina has explained very well on the context of the European chemical industry, it provides jobs for over 1 million people, direct jobs. It has over 500 billion euro in sales, but also there are some drawbacks. We have the chemical industry have a bad image considering the high pollution that it has. So basically, one of the industries that we need to tackle to be able to reach the European climate targets is the chemical industry, and try to produce chemicals, intermediates in ways that we can reduce the overall CO2 emissions. So basically, in Photoelectrochemical, we are targeting these 3 different sustainable development goals: SDG 7, SDG 12, and SDG 13, with the idea to reduce the reliance on fossil fuels, to be able to showcase that we can do sustainable manufacturing, and also because our project is basically targeting the use of solar energy. We are very much interested in the collaboration between European countries and African countries as well. If you look at the greenhouse emissions, so it's clear that the industry is a main culprit of this. And if you look at the different CO2 emissions within the industry, you can see that there are many of these that could be reduced by using sustainable processes as well. So in terms of greening the chemical industry, this graph shows a little bit of a good summary of what you can actually do. Okay, so you can just optimize processes and the energy of the processes, which means that it is low risk, low cost, but also very low potential for CO2 reduction. With just optimizing processes, it is almost impossible to reach the climate energy targets. The second phase could be the large introduction of renewable energy into the supply for the chemical industry. This has a medium cost, medium risk, but also only medium potential for CO2 reduction. Basically because there are processes that even with electrification, they cannot be fully decarbonized. So therefore, the last step, it is really to produce breakthrough technologies to reduce CO2 emissions. And that's basically what the IPCC calls the negative emission technologies. In our case, we are basically looking at this type of technologies where we are trying to use CO2 to produce chemical feedstock. If you look at the traditional fossil-based petrochemical industry, you can produce all these different platform chemicals. Okay, you have the typical methanol, the ethylene, propylene, benzene, etc. All these are the building blocks for most of the chemical products that we are using nowadays. On the other hand, you have on the right side of the image, you have what we call the bio-based petrochemical industry. So in this case, you can use some of these modern technologies, like using biomass gasification, using water electrolysis, steam methane reforming with carbon capture, so that basically to produce the blue hydrogen. So all these can lead to similar products. But still, there is a lot of CO2 that is required for these processes. So the project vision that we have in Photoelectrochemical is basically this integration of 3 different types of reactors, 3 different technologies: a photoelectrochemical cell, a photocatalytic reactor, and an electrochemical system. And we are trying to develop, optimize, and scale up this integrated system to showcase that we can produce ethylene in kind of a large scale. Okay, so the target that we have for the project is about 500 kilos of ethylene per year, and the only inputs that we require for the process is basically the water, the CO2, and sunlight. Our objective is basically to use concentrated sunlight, and basically we will have these sort of concentrators with 2 different focal points, one with high concentration for the first reactor and one with a lower concentration for the second reactor. And basically we are aiming at producing these different chemicals through the different reactors. As the first speaker has mentioned, we are taking into consideration the sustainability by design. So basically through all the different processes, all the materials that we are developing, we are looking at the life cycle analysis and the impact that they have throughout the manufacturing of the chemicals and also the implementation in the process. So here are a couple of aspects that we are looking at. So basically, we are supposed to be delivering sunlight to chemical conversion efficiency over 7%, with a performance loss of less than 5% 1,000 hours. The reason why we selected ethylene as our main target, it is because it is one of the main chemical feedstocks for the chemical industry. It is used in the plastics manufacturing and in many other industries, but also because it's the highest value, the highest chemical with the value among the different products that you can obtain out of CO2 reduction. However, even though the main target is ethylene for the demonstration, what we are really interested is developing the different components to fabricate reactors, materials, so that basically you can have flexibility in terms of the final product that you are aiming to achieve. Depending on the selectivity of the different reactors, you can have a wide variety of different products that they are used in the chemical industry, but also in other types of industries that could be of interest as well, through just tuning a little bit the materials that you have in the different reactors. So basically, our starting point on the different reactors were systems that were already available in the Barnes lab. So for the photoelectrochemical reactor, this work is done at EPFL with Professor Sophie Hausner. So we started already with a system that was working under high concentrated light and was able to produce about 800 milligrams per hour of hydrogen. Our goal was to scale up the system and to make it more robust and also more stable. But also our aims is to try to really reduce the amount of precious metals that you're using in those systems. In the system that we had at the start, basically we were using ruthenium iridium oxide materials. We were using also platinum as your cathode material. So really there were a lot of aspects that could be improved in order to basically try to reduce the amount of precious metals into the system. At the moment, it's been less than 2 years for this work. We have already reached our target of producing this 8.3 grams per hour of hydrogen. Okay, so this is what we have in these different plots. Okay, so this is the large-scale reactor in a 2-month continuous operation, and it produces roughly about 12 non-liters per minute of hydrogen, which relates to the expected target. So basically, we have already a system that is producing the amount of hydrogen that we require for the integrated system. Also, for this reactor, we have also adapted a little bit the reactor in a smaller scale to be able to use concentrated light to produce solar syngas. Okay, so it's a mixture of carbon monoxide and hydrogen, as the previous speaker has mentioned. In our case, our system has shown to have a record efficiency of solar to CO of 17%. In the case of the photocatalytic reactor, our baselines were also these two type of systems, these two types of photocatalytic reactors that were developed in the Polytechnic University of Valencia and also at the University of Amsterdam. So looking at the literature, one of the most important aspects for us was to try to really reduce the operating temperature. So basically try to increase the photocatalytic effects and decrease the photothermal effects of the material, while also getting really the selectivity that we require to produce the carbon monoxide, and of course scaling the reactor into reaching the targets that we require for the final ethylene production. So at the moment we have been working on different types of reactor designs, and this is some work from the University of Amsterdam, that they are developing different types of photocatalytic reactors that we could use. So far, this part has been quite challenging, and we are looking at different types of reactors that could be scaled up to meet the targets. Also, in terms of the materials, we are looking at different types of materials that can produce the selective photocatalytic CO2 hydrogenation. And this work published by the Polytechnic University of Valencia this last year showed that these type of end-dome graphene have very good selectivity towards carbon monoxide, but still the production rates have to be improved to meet our targets. In terms of the third reactor, the CO electrolyzer, so the work is basically led between the Helmholtz Center in Berlin and University of Szeged. And we were basing our systems on CO2 electrolyzers that have been developed in the University of Szeged for the last couple of years. Also looking at the literature, we saw that there are some interesting examples of CO to ethylene conversion that we could try to mimic, and basically we could try to reach the expected target for ethylene using some of these systems. The main difference is that most of these data that you have in this table is coming from really high temperature CO electrolysis, and that's what we wanted to achieve, to avoid as well, to try to work around moderate temperatures instead. So far, we have developed our own CO reactors, CO electrolyzers, and we are working on trying to improve the efficiency towards ethylene. Okay, so we have all the system with all the controls to be able to monitor the liquids and the gaseous products as well, so to really measure the overall selectivity of the system. And also what our colleagues in Berlin are doing is they have modified also one of the cells so that they could do in situ X-ray spectroscopy at the synchrotron. So basically we could learn about the effects of the operating conditions in terms of the materials, the electrocatalysts that we are using for CO2 ethylene conversion. Of course, what we wanted to do is the integration of these different reactors, and this is done by DLR. So we have started to produce the process flow of these different integrated systems, where basically we consider not only the individual reactors, but also how to connect the reactors between themselves, if we need compressors, if we need pumps. So all this is taken into account into the overall process simulation. And of course, we are also very interested, and also again linking with the first speaker, about the digitalization. So we are looking at these multi-scale multiphysics modeling that we could basically go from really doing calculations, performing calculations to get thermodynamic and kinetic parameters of the catalyst that we are producing down to really the process and the plant simulation. So in order to achieve also the stability performance that we require over 1,000 hours, we will be conducting two different types of testing at the DLR facilities. So we'll be conducting continuous testing of about 100 hours for 24 hours a week, 24 hours a day, and also to do stress tests of 8 hours a day, switching on and off, so that basically we can mimic these stress conditions that you would require for performing stability tests over 1,000 hours. So in the project, we have envisaged basically all the way from the starting point that we started at TRL 3 with these different reactors that we had in the lab towards TRL 5 and 6, where we will have the demonstration of the integrated system in the DLR, and also how to basically move towards potential commercialization. And again, not really on the integrated system for ethylene production, but on the different components, the materials, the electrocatalysts, the membranes, the reactors, etc. We are required to basically expand this into an overall sustainable industry. So the project, we are 14 partners across 8 countries, like in SunCoChem, and we have expertise in the different aspects of that we require for the project. So we have a couple of partners on the catalyst design, manufacture, and characterization. We have some partners on working on the designing the reactors, building the reactors, and also integrating the reactors into a system. We have partners dedicated to modeling as well, and EPFL missing here. Okay, and modeling not only on the materials side, but also on the process simulation. Partners dedicated to the exploitation and commercialization, so they will be the companies that are involved in the project. Of course, this life cycle analysis and sustainability, that's very important to meet this design by sustainable design that will require also to develop sustainable processes, and through the communication of the project results. Of relevance, as you can see here, is that we have one partner from Uganda, from Africa, Jambo University, that apart from being involved into the technical part of the work, developing catalysts as well, we are very much interested in extending this collaboration between Europe and Africa. And related to that, we are very happy to announce that on the 4th of November, we will do a workshop in Uganda dedicated to innovations for the new age of the chemical industry, where basically our idea is to showcase these different technologies for solar to fuels conversion, or solar to chemicals conversion, that you can use basically using sunlight, water, and recycled carbon dioxide. And basically this event will be aligned by another conference on renewable energy that is organized by the Minister of Energy in Uganda. So of course, as you can imagine, this is a work by a lot of people, and this picture shows just part of the team that we were able to meet for the first time back in November in Dublin. And we are very much looking forward to meet again in a couple of weeks in Hungary as well. So with that, I'd like to thank you all and thank you for listening, and I'm very happy to take any questions. Thank you.
Thank you very much, Paul. Nice presentation as well. And I'm liking the pictures of the things that you are showing. Very nice. Okay, now I'd like to give the floor to Claudio Ampelli. Claudio received his PhD from the Faculty of Engineering of the University of Pisa in Italy. Since 2019, Claudio is an associate professor of chemical plants and technologies at the University of Messina. He has a wide experience in electrochemical engineering and catalysis, especially in the development of nano-engineering, engineered electrodes, and the design of unconventional photoelectrocatalytic devices for electrification. He is currently the principal investigation of the DECADE European project from the research unit of ERIC, the European Research Institute of Catalysis. So,
So, good morning. Can you hear me?
Yes.
Okay. So, thanks for the kind introduction, Maria. I'm very happy to take part in this webinar. Thank you so much for the invitation and for giving me the opportunity to show some of the research activities we are doing in the framework of DECADE project. So I want to share also with you some concepts regarding energy and chemical processes. So today I represent ERIC, that is the European Research Institute of Catalysis. I deal with photoelectrocatalytic stuff, so electrodes and devices that work as artificial leaves. So in a more general vision, these are systems that enable small cleaner molecules like carbon dioxide, water, nitrogen, so to produce more value-added products, not using fossil fuels, but using renewable energy sources. But let me first introduce a new concept in electrocatalysis. There's a growing interest in electrocatalysis due to the increased availability of electricity, so produced from renewable energy sources. But the term electrocatalysis has now assumed a different meaning with respect to the past. It has a main role in the future challenges for the production of energy, for the reduction of CO2 in the environment, and for the development of novel industrial processes. So I want to remark that electrocatalysis is different from electrochemistry, and also quite different from electrochemistry in the presence of a catalyst. So we can state that in an electrocatalytic process, highly reactive species are formed, so electrons, holes, radicals, due to the application of an electrical potential. So these species can drive a chemical reaction, or better, two chemical half reactions on the surface of well-designed electrodes with improved properties, better if they are nanostructured. which are designed on purpose to increase selectivity towards specific compounds. So this slide shows schematically how electrocatalysis can accelerate the transition from a linear to a circular economy. As you can see here, the current economy refers to a linear model based on the use of fossil fuels, both as a source of energy and a source of carbon, so with an avoidable production of CO2. But CO2 emissions can be in some ways mitigated with technologies like carbon capture and storage or other sequestration methods, which don't change the linear approach but progressively go towards an indirect circular model. So final division is to go to a full circular economy where electrocatalytic processes are able to produce carbon compounds for chemical industry, and the produced CO2 is then recovered and transformed back to useful products in artificial lift type systems. So the artificial lifts are the core technologies to enable this sustainable future. So while the largest part of electrocatalysis focus on simple reaction, for example, the two-electron reduction of CO2 to carbon monoxide or to formic acid, the challenge is instead to realize more complex conversion of CO2 or other carbon sources, so leading to active intermediates and multi-carbon products to build a sort of petrochemistry equivalent framework. So this figure shows this concept by starting from primary electrocatalytic reaction that involve the conversion of small molecules, so water, CO2, nitrogen, or methane, and combining those with the electrocatalytic conversion of bio-derived molecules. It is possible to produce a wide range of products forming the skeleton of a new chemical production that we can define as e-chemistry. So after this premise, let me introduce the European project DECADE. DECADE acronym stands for Distributed Chemicals and Fuels Production from CO2 in Photoelectrocatalytic Devices. I'm the principal investigator for the research unit of ERIC with the University of Messina associated as a third part. So the project started 2 years ago. The aims of DECADE project are well in line with the novel aspect I discussed before, and also with the vision aspects of many European initiatives to contribute to a more efficient and sustainable energy scenario for chemical industry and for the climate neutrality. So the general objective of DECADE project is to develop a novel photoelectrocatalytic device engineered to use feeds like waste CO2 and bioalcohols, bioethanol or methanol, so to synthesize more valuable products. I have to say that the dark reactions are very ambitious. I will discuss them in the next slides. So the project is based on a novel approach that can represent a breakthrough towards a full circular economy, so to lower carbon footprint as I have described before. So what is the novelty? What are the challenges to face in DECADE? So the key element is to design and realize a device that exploits both the side of the cell and produces the same chemicals in the anode and in the cathode. So that's the first innovative challenge of DECADE. At the anode, we want to avoid the oxidation of water to oxygen, which usually limits the actual energy efficiency. Oxygen is often considered as a waste product in artificial lift. So the idea is to integrate the conversion of solar energy with the utilization of bio-derived products coming from biorefineries. An important point is to develop flexible solutions to meet the requirements of multiple markets in terms of chemicals and fuels. And also the project allows for the realization of a first lab scale device, so in a compact configuration to reduce energy losses. But this device will then be scaled up to be used as an artificial lift with a larger electrode surface area. And of course, all is in line with the process intensification. So in general, to realize an artificial leaf, many options exist. I report here two graphs of efficiency versus the complexity of the system for the production of hydrogen on the left-hand side and for the production of carbon solar fuels on the right. So the classical option is to use photoactive particles in slurry that usually do not provide high efficiency. Then the other option is a PEX system with separation of a photoanode and the cathode for oxidation and reduction reaction. And finally, an integrated system, so a photovoltaic cell coupled with an electrochemical cell. So although the higher complexity of this coupled system, the state of the art clearly indicates a higher efficiency for these systems and also higher current density and stability of materials. And for this reason, in Decade project, we decided to go for this option. So more in detail, we work with one of the main chemicals produced in biorefinery, that is ethanol, bioethanol, associated with carbon dioxide emissions coming from biorefineries. As said in the previous slide, we combine the use of a photovoltaic cell with an electrochemical cell, so to get higher performance. And this is the novel part. We want to produce the same chemicals from both sides of the cell. So at the anode, instead of the classical water oxidation to oxygen, the reaction is the ethanol oxidative dimerization to form ethyl acetate. While at the cathode, CO2 is reduced to acetate, which is then transformed on site by reacting with ethanol to form ethyl acetate, so which is the same product obtained at the anode side. Of course, at the anode, we expect also the formation of a formate, which in turn will esterify with ethanol to produce ethyl formate. But that's not a big problem because the mixture of ethyl acetate and ethyl formate in ethanol can be used directly, so without the need to separate, as a green solvent, as a fuel additive. So this concept is not used only for ethanol, but we can also use for methanol. And in fact, there is one of our partners, a company that is highly interested in this application for a potential use in methanol plants. So for the project, we have created a consortium trying to introduce all the components needed. See here all the partners involved. I want to remark that there's no information in literature on optimized catalysts for this target reaction that we propose in Decades. So the partnership has top-level scientists in the area. There's a strong participation of industry. There's a series of companies involved in the development of materials, in market assessment, life cycle assessment, and other international validation system, and also companies that will test the device in environmental relevant conditions. So there is also an international collaboration with Japan, with Professor Domen, who is one of the main experts in the world on photocatalysis and photoelectrocatalysis, who acts as sort of an external advisor to allow the best possible benchmarking. Last week we had the 24 months meeting in person in Catania. We had a great discussion among the partners. The preliminary results are very promising in terms of new electrocatalytic materials. We also have a first version of the prototype. So more in detail about the activities of ERIC and University of Messina that regard the design and construction of the lab scale prototype, and then the experimentation on the electrodes, anodes and cathodes developed by the other partners, and then the coupling with the PV cell, which is optimized and produced by the research center of Jülich in Germany. And finally, we are also involved in the upscaling of the prototype together with the ICTech company. So we have started from TRL3, but the novel PEC technology will be developed up to TRL5, so the prototype testing under environmental relevant conditions, using alcohols and waste CO2 as the feed. So going briefly in some specific scientific aspects, we are currently studying in Decade the presence of organic solvents like ethanol or methanol, unfortunately, introduces some practical problems when using conventional gas diffusion layer substrates, which have a certain grade of hydrophobicity, so to keep away the water electrolyte, as you can see in this figure. But unfortunately, these gas diffusion layer substrates don't work properly in when ethanol or other organic electrolytes are present, with consequent flooding of the gas diffusion layer and decrease of the gas transport properties. So we are trying to solve these issues by modifying properly the engineering of the electrodes and the cell configuration. So in conclusion, the aim of Decade project is to develop next generation of photoelectrocatalytic devices, so to use CO2 and bioethanol for the production of green chemicals and fuels, and also to explore the potential use of this technology to improve circular economy, to lower carbon footprint in chemical and energy processes. So I want to acknowledge again the organizers for the invitation and all of you for your kind attention.
Thank you very much, Claudio. A very interesting presentation indeed. So now we will stop for a while the coffee. Yes, since we are pretty behind our schedule, instead of devoting 10 minutes to this coffee break, we will be just out 5 minutes in order to recover the time that and the delay we are accumulating. So see you everybody at 11:30. Okay. Okay. So 5 minutes of coffee break. See you soon. So, sorry everyone for this short coffee break. We are trying to recover some time because we are accumulating a little bit of delay. So the objective with this also is to have some time at the end for questions and answers. So the audience can express themselves and clarify and some of the questions. Now, I guess the speakers are. There's a bit of. So I would like now to present or to introduce Siglina Peratone, who will start the second session of the day, of the one. Siglina Peratone obtained her PhD in chemical science in 1988, working on the photophysics and photochemistry of supramolecular systems. From 2001, she joined the now she is full professor of industrial chemistry. She coordinated many EU projects, and she is currently coordinator of the EU project Ocean on new industrial electrocatalytic paths of CO2 conversion. Siglina, you start when it's yours.
Good morning. I will present today the data of the European project, Ocean project, dealing with oxalic acid formation from CO2 using electrochemistry and going to a demonstration scale. This means involvement of companies able to go to a demonstration scale. The project is at the end. We will finish in July this year. Next slide. Okay. Which is the project objective? With the increasing share of renewable electricity in the overall energy production, there is a renewed interest in electrochemistry in industry. As you know well, with the electrochemistry, there are several processes based on electrochemistry. But now there is a renewed interest in the industry because there is the possibility to have a clean and carbon neutral energy source to drive chemical reaction. Despite the electrochemistry and electrosynthesis, the application of electrochemistry synthesis in industry are really limited. So there is the need to go for a renewed application of electrochemistry using CO2 and renewable energy. And the Ocean project has had the objective to provide a proof of the economic and industrial feasibility of the technology to convert CO2. We will see now. Which are the opportunities and challenges to drive directly through electricity chemical reactions, because this allows to use less expensive starting materials. We can start from CO2 and simply from water. Then we can go to less aggressive process conditions. We can replace polluting chemical reactions, makes more environmentally friendly. And we will see now, in the case of in a particular case, how it's possible to transform CO2 to formiate oxalic acid and formic acid, to go to ethylene, glycol, and glycolic acid, which are the precursors to produce polymers. So we can convert CO2 in mild conditions using electricity to have polymers like polymers used in a substitute to polyethylene terephthalate for plastic bottles. So this is the value tree starting from CO2. This means one carbon atom to go to formiate, formic acid, always one carbon atom, oxalic acid, to go to glyoxylic acid, glycolic acid, glyoxalate, and so on the top of the tree. Which were the specific objectives of the of the project. So it's clear we are going from CO2 through small molecules like formic acid, oxalic acid, to polymers. So it was important to demonstrate the industrial feasibility of the electrochemical reduction before in a demo cell, and then to go to higher TRL level. This was possible using the collaboration with industries, with companies like RWE in Germany, where actually the demo plant is operative. From it's working from 600 hours using 250 grams of CO2 per hour. To produce the intermediate oxalic acid. It was necessary to have a stable catalyst. This was developed during the 4 years of the project. And then the integration starting from C1 to C2 or products to go to polymers. This is the demo cell. This is the demo cell developed at Advantium for the production of formiate, the first intermediate. This is a 100 square centimeter reactor, and actually I have also a video, but you can find this on YouTube at RWE, which shows the scale up of the cell to go to industrial scale. Thank you.
Very much, Silinda. Nice presentation as well, and we have recovered some time, so thank you for that. Now I will jump to Simeris Hernandez, our next presenter. Simeris is the Recode Technical Coordinator in the Italian Institute of Technology, and she's also Associate Professor in the Politecnico di Torino. Please, Simeris.
Okay, thank you. So thank you very much for inviting me to this webinar today. I am very happy to be here with all the cluster of Road to Green Chem. And today I will present our activities related to the RECODE project that is related to the recycling of carbon dioxide in the cement industry at a TRL6 demonstration scale. And as you may know, or you will learn today, the RECODE project particularly focused on the emissions of the cement industry, which within which there are several sources that can contribute to those emissions, from the extraction of the raw material to the transport of the finished product. However, the most significant contributions comes from the transformation phase that of the raw material. I don't know, okay, that is made in the clinker of the plant. And this phase is the reason why the cement industry contributes to about 5% of the anthropogenic CO2 emissions, with a carbon footprint that is close to about 1 kilogram of CO2 emitted per kilogram of cement that is produced. There are two approaches that can be employed to reduce this carbon footprint in the cement industry. The first one is the reduction of the clinker factor in the transformation step, which is the main responsible for the CO2 emissions in this industry. But this will change the quality of the produced cement. And on the other hand, the other approach consists on the implementation of carbon capture and sequestration technologies. Therefore, a promising alternative is the combination of these two approaches and produced cement additives to enhance then the mechanical properties of the material. And so, for this purpose, we face the challenge of optimizing the energy consumption related to the carbon capture and utilization technologies, which are the very energy intensive processes. So here in the concept of the RECODE project, we aim to recycle the CO2 that is produced as a flue gas from the cement industry that constitute about 10 to 25% in volume of this flue gas, and this will be captured and reused to produce value-added chemicals like additives for cement formulations or other materials that can be used, for example, as concrete fillers, in order to improve the quality of this final product of the cement industry. So in this way, we aim to do a circular economy approach that is able to utilize the CO2 as a raw material in the manufacturing process of the cement industry. Our final goal is to make the cement industry able to contribute to at least a 20% of reduction of the CO2 emissions in the medium to long term. And we will do that, and indeed we are doing that, thanks to the contribution of different partners, starting from the large industrial partner Titan that is hosting actually now our demonstration plant, 5 small medium enterprises and 7 research centers, all that are located all around Europe. Here you see our demonstration plant that had been already installed at Titan facilities in Athens, in Greece, and now we already started our demonstration campaign that will end in July of this year. This is the concept in detail, the technical concept of our project. So in this scheme, you can see clearly how the captured CO2 that comes from the flue gases of the plant will be absorbed by the means of ionic liquids, and then this will be desorbed and utilized as pure CO2 into different kind of processes for its transformation to useful products. A first part that is related to the work package 4 of our project, that is related to the precipitation and crystallization of this CO2 together with a source of nitrogen in order to produce nanocalcium carbonate and ammonium chloride. And then we have 3 different routes of electrocatalytic processes and catalytic processes that will exploit the CO2 for the production of useful added valued products like formic acid, oxalic acid, and glyoxylic acid, and later glycine. So our project in the long path of these 4 years of project, we have been developing our technology from starting from TRL 3, then passing to the demonstration and proof of concept at TRL 4 and 5, and finally we are now in the phase of the demonstration in the demo plant at TRL 6. So starting from the part of capture of the CO2, here you can see the first results that were obtained at TRL 4 in the mini plant at the facilities of the Vosges. And here we demonstrate to be able to capture CO2 and to obtain a purified CO2 with a quality of higher than 99% in volume, with a separation efficiency of 75%, and without the activation for at least 220 hours. And this was all done thanks to the development of a new kind of ionic liquids that are being actually utilized in our demonstration plant and that are right now treating 100 cubic meter per hour of flue gas that arrive at the plant at a temperature of 120 Celsius degrees, and that contains concentrations that are as low as 10% in volume of CO2. And the idea, the final goal, is to produce 8 cubic meter per hour of purified CO2 with this purity of 99%. And here you see some pictures of the plant that is already installed at Titan facilities. Then, regarding the conversion of this CO2 in the first kind of technology, the calcium carbonate precipitation system, we have also started from TRL 3 at Politecnico di Torino and CERT, and we have optimized the process from different points of view regarding the additives concentration, the calcium concentration, the flow rate, so different operative parameters in order to be able to control the different crystalline structures and the size of the structures that we obtain. And we have also optimized 2 different kind of reactors. A first kind of hollow fiber membrane-based precipitator that enhance the contact between the gaseous phase CO2 and the other precursors of the calcium carbonate. And we have also developed a new concept of packet bed reactor for this crystallization precipitation system. Finally, here you see the plant that is installed actually at Titan facilities that was constructed by MET. And here our goal is to have at 100% of capacity a final productivity of 3 kilograms per hour of calcium carbonate with a CO2 conversion higher than 20%, and the possibility to produce additionally another valuable product that is ammonium chloride. Then we are also evaluating the impact of these products in the final cement plant product, that is the concrete, and we have already proved that substituting the clinker with 1 to 2% of our nanocalcium carbonate particles, it was possible to lead to up to a 5% of improvement of the mechanical properties of the concrete. Regarding the electrocatalytic conversion, we have also passed through a process of optimization and scaling up process. So we have first developed a CO2 simultaneous compression and dissolution system in order to enhance the energy efficiency of the dissolution of the CO2 in the liquid electrolyte. We have also optimized the catalysts that had been employed and will be employed in our electrocatalytic reactors. For example, here you see the catalyst for the conversion of the CO2 to formate that have a Faradaic efficiency higher than 99% and is based on bismuth, so based in non-noble metals. And here you see our TRL 6 plant that will be constituted by a stack of electrocatalytic reactors with electrode size of 0.1 square meter. And the final goal here that we are achieving and we are demonstrating in the Titan plant is the production of 0.5 kilogram per hour of formic acid, 50 grams per hour of oxalic acid, and 0.2 kilogram per hour of glycolic acid. And these chemicals can be, and we are also making experiments to demonstrate the possibility to exploit those products as chemical additives, as admixture in the cement, or also for other applications. Then we are also working in the modeling activities and integrating from modeling and from the control process of the process point of view all the units that had been developed during the project. So we have done CFD modeling, for example, of the absorption columns. We have done process modeling of the ionic liquid-based CO2 capture process, and also modeling of the electrochemical processes in order to optimize the operative conditions and achieve our final goals. Last but not least, from the environmental point of view, we are performing also life cycle assessment and techno-economical analysis in order to evaluate the reduction of the actual emissions of CO2 of the cement industry. And for example, here you can see in this picture how we are able to reduce the emission of CO2 in the cement just by the production of our nanocalcium carbonate and ammonium chloride products. And with this, I just thank you for your kind attention, and I leave you here with a picture of some years ago. It was the first year meeting of the project when we were in the Taita plant, and we hope to be there again in July of this year to celebrate the final meeting of our project. And just keep tuned. We will also make some nice dissemination activities so that all of you know what came out from our final results and our final demonstration campaign. Thank you very much.
Thank you, Simelis. Very clear explanation of the concept. And yes, I hope you can meet again soon. It's always very nice to meet physically again. So now we will start with the third and last session for today's webinar, which is composed of, we have one presentation but two presenters. The two presenters of the last presentation are Julia Machado and Horacio Salah. Julia is an environmental manager with a master in water and coastal management. Currently, she is a Marie Slodowska-Curie PhD fellow at the SunCoChem project and also political science PhD student at the National University of Cardiff. Horacio is, like Julia, a SunCoChem early stage researcher and a PhD researcher. And he's doing this at the Technical University of Valencia. So, Julia and Horacio, I think the first one is Julia. So, whenever you're ready.
Thank you for the nice introduction, Maria. We are very pleased to be here today representing our project and our colleagues, me and Horacio, as you can see. So, good morning to all of you, and thank you for being here today and seeing our last presentation, which will be divided in three parts. Next, please. So we start our presentation by presenting the SunCoChem project and its range of photo-assisted technologies, and then we move to the study case, as today we are going to be focusing on photothermal CO2 reductions because the SunCoChem project covers a wide range of different technologies, and today Horacio is going to be presenting one of them, and then we close our presentation by connecting the two with our final remarks. So differently from the other projects, SunCoChem is a doctoral level Marie Curie ITN project, which is an innovative training network, which aims to train 15 early stage researchers in all areas of the solar chemical supply chain for its advancement. So the project is organized into 4 working packages. Next, please. So yeah, the 4 working packages that encompass photoanode and photocathode studies, advanced characterization, and also include technology deployment. So these are divided into tasks and deliverables between the consortium partners according to their expertise. As you can see here in the text boxes that we included some of the work that is being developed within our consortium and by the 15 ESRs. So SunCoChem aims to convert water, CO2, and even organic waste into solar chemicals and solar fuels, such as hydrogen, ammonia, and alcohols, and many other products, interesting and high-value products, and important energy vectors or chemical base materials for several industries. However, there are several technological challenges in terms of solar irradiation, type of reactor, the type of system, efficiency, and scalability, as the other presentations already discussed. This is why we focus on developing and improving the different photocatalytic, photoelectrocatalytic, and photothermal transformation in a synergistic approach. So connecting the different disciplines involved is fundamental to overcoming the technological, but also the political limitations, and opening doors for the development of these new alternatives that will assist Europe to reach the climate emissions and everything that we are discussing today about the EU Green future. And one of the options is what Horacio is going to be discussing now.
Right, so good day, everyone. As Julia just said, I'm going to take over the second part of this presentation, and I'll focus on photothermal CO2 reduction, mainly to CO in our case, as this was the main product and the objective of our project. And to be even more specific, we're going to focus on metal species deposited on nitrogen graphene or graphite carbon matrices. So just to understand better what photothermal catalysis is, compared to photocatalysis, it's not directly dependent on the charge separation about light irradiation, but rather by nanoheaters induced by light irradiation. So what this means is basically that it's a lot closer to the classical thermocatalytic systems that we already have a lot of progress out there in the scientific literature, and also there are tentatives of bringing it out. So technically, we're not starting from zero with this technology. The only difference is that instead of the conventional heating, the heating is actually obtained through light irradiation and at the nanoscale level. So just to understand better how this happens, we're going to take two cases, let's say, and in the figure in the middle, we will consider non-plasmonic metals deposited on semiconductive support. So in this case, there is no obvious synergy between the support and the metal nanoparticles, but the heating is achieved through phonons rather than any other charges. And not so obvious synergy could be obtained through the thermal conductivity of the support, hence minimizing any heat dissipation. A very similar one would be with plasmonic metals, in which the nanoheating is achieved exactly through the same way, through phonon scattering. But this time around, due to the surface plasma resonance and the decay of this resonance, hot electrons could be produced, which can be injected into the bands of the semiconductive support through the Schottky junction. And the last but not the least would be a junction between two semiconductive media, in which case the nanoheating would be achieved through charge recombinations. And in case of proper band alignment, they can the supported moieties can also act as recombination centers for both the support and itself. So regarding our choice of material, we are synthesizing graphene or graphite carbon scaffolds from natural polysaccharides or from natural acids. And this is very convenient since by choosing different precursor, we can obtain different heteroatom dopings, or by combining the different polysaccharides in the synthetic procedure, we can obtain several heteroatom dopings on the same scaffold. So it's both cheap and very simple synthetically. Why graphene though? Well, at least in our system, it is very convenient since if both the bands of the metallic species, the D bands and the pi bands of the graphene, can interact synergetically to give quite outstanding catalytic results. And moreover, with the doping that I previously mentioned, we can help a lot the substrate capture, which enhances the catalytic output quite a lot. So going to a more specific study that we disseminated this year, we obtained from Kitazan and from different metallic precursors our scaffolds with a very easy procedure. We beaded the polysaccharides already impregnated with the metal. We dried them and then pyrolyzed them to obtain those very high quality catalysts with a very good dispersion and also good particle sizes. So jumping right into the catalytic output of these materials, when we consider cobalt iron, and this is a system that's been has been investigated quite a lot in the past years, at least in CO2 reduction. The catalytic output is good. In 24 hours, we can achieve around 40% conversion, and What's very interesting to note this time around, since the technology is already well known, is the light enhancement. So this is the main objective of photothermal studies, at least from a fundamental point of view right now. So the light enhancement is around 80% compared to the dark conditions, which is quite significant. And we decided to investigate this further. But as you can see on the right, in red is the selectivity for methane, which definitely didn't reach our objective, since we actually wanted major CO selectivity. So CO is the rate determining step. So we needed to think about how to actually favor a less thermodynamically stable product in the system. So the first thing we thought about was just to reduce the metal content of the in the catalyst itself. So we actually reduced it by more than 100 times. And interestingly, we did indeed achieve almost complete conversion to CO. The dispersion of the metals and the catalytic support were still very fine, with particle sizes lower than 2 nanometers. So right now we can talk about clusters. And what's even more interesting is that the catalytic output only decreased by half, despite decreasing the metal content by more than 100 times. So this was quite an interesting system that we decided to go very deep into studying. So the next part was just to figure out what was giving the light enhancement. So we considered two different systems. One with the isolated iron clusters on nitrogen graphene, and one with cobalt. And we could observe that indeed in iron, despite the activity being a lot lower, something that is already well known in the literature, as iron is not as good in regular hydrogenations as cobalt. The light enhancement was more than double. So we needed to investigate if this was indeed photothermal or photocatalytic, as we deduced before that it was actually iron oxide or graphene. So we needed to know if it was the third case that I mentioned in the introduction, which is a junction between two semiconductive media. So we assessed the activation energy in both dark conditions and light conditions, and both activation energy has very close in value, which was reported before for photothermal catalysts. But interestingly, the photoresponse of the iron analog was significantly higher than on a bare support or the cobalt analog. So indeed, there is charge separation involved in this mechanism. The catalyst was inactive in the absence of UV light, which is not good news if we consider to later, let's say, use this for solar light, but it was a good clue for us in understanding the mechanism behind it. And the last clue was given to us by transient absorption, where we saw that despite having a higher photo response, the iron analog had a much lower lifetime for the charges in both higher lived and shorter lived components. So with everything together, we were confident enough to say that this is indeed a photothermal mechanism, and our catalyst is doing photothermal CO2 reduction. So just to conclude this small little project that was very interesting, and I think brings quite a good contribution to the field. We need to look for synergy between the support and the moieties that we are indeed depositing on the support, besides the possible thermal conductivity synergy. The particle size directly influences the selectivity. The main contribution when it comes to light activity was given by iron. And also we confirmed that it's indeed a charge recombination mechanism. So now I will give the microphone, which is virtual, but to Julia to finish her remarks. And
yeah, so we are talking about synergies that are within the system, but we also see that these improvements are part of an increasing research and innovation effort towards this transitioning to a greener society. And as I mentioned before, there are several solutions in the market and many more to come if research and innovation advance, and if the right incentives and measures are designed and implemented, which will be filling the blanks that we have, both scientific, technological, and regulatory. We know that we are living challenging times more than ever, and we know that maybe they will be able to push these needed changes. So reinforcing what we discussed here today, political technological focus should rely on this inexhaustible solar energy and on finding solutions for the use of the rare metals and the critical raw materials that are normally used for these systems, and on improving the design of the systems and the devices, on considering water and land use and in more sustainable approaches, as all the other projects commented. But simultaneously, we need to work on creating appropriate policies to push for competitiveness, on developing well-structured collaborations like the project that put all these other projects together today, and focusing on interconnected proposals that consider the quadruple helix and the fair transition. I think that's the final message that we wanted to bring today. Next question, please.
Sorry.
So we would just like to thank all of our European and international partners, which are part of the SunCoChem Consortium, and also thank all the other ESRs for helping us putting together this presentation for you today, as we are here representing the 15 ESRs and the different projects that SunCoChem covers. Thank you all for your attention, and invite you to visit our website to check our presentations, our papers published, and join us in our social media. Thank you.
So thank you very much, Julian and Marati. That's a nice group of early stage researchers, and I'm sure you're producing good materials and articles. And so please, to the audience, please visit their webpage. Yeah, if you're interested in this topic. So it seems that finally we will have 10 minutes for questions. Okay, I have a set of questions for every one of the presenters. We'll go in order of the presentations, in order of the presentation according to the agenda. So the first one will be for Miriam Dia. Miriam, so usually the main limitation of molecular photoelectrodes devices is their long-term stability. Which is the approach in SunCoChem that you are following to address this issue?
And the approach of SunCoChem is to address the long-term stability of the device, you say. Yeah, in fact, what we are trying to do is to, for instance, concerning the development of the photoelectrodes, we are doing a multi-heterojunction of different kinds of materials, integrating semiconductors, molecules, that act as a photoabsorber and catalyst. And here an important issue is that they are less stable than just the use of semiconductors alone. The problem with semiconductors is they are not, they have very bad performance in terms of catalysts, no, as used as catalysts. So we are trying to immobilize those catalysts with covalent functionalization that is compatible with drastic conditions, no, to avoid the leaching of those molecular catalysts. And this is one of the approaches that, for instance, we are trying to follow for long-term stabilization.
Great, thank you very much, Miriam. Okay, our next question will be for Paul. Yeah. So what do you think? How can the flow photochem process compete with other processes for the ethylene production?
So as I mentioned in the presentation, we are not really trying to produce ethylene using our integrated system reactors. So what we do is basically try to develop the individual reactors so that we can produce a wide variety of different compounds. And of course, for the purposes of the project, we had to choose one chemical for demonstration purposes, and that's why we chose ethylene. But at the moment, it's clear that with competing technologies, depending on the combination of the reactors that we have, it will not be competitive. Likewise, I think it's important to realize that the ethylene production methods that we have now will not be sustainable. Okay, so at the end, we are competing not with the actual processes, but with the ones that will be there in 20 years that will be based on electrochemical transformations in maybe biological processes as well. So at the end, any comparison with the different processes that we will have there have to be made with competing technologies that will be there in 20 years, not what we have now as well.
Thank you, Paul. Thank you very much for your answer. Okay, for Claudio and Ampelli. So during the presentation, you mentioned that the device you are developing within the project consists of a PV cell coupled with an electrochemical cell. How are you going to integrate these two systems? And I also would like to know what is the target? What is your target for the photoelectric efficiency? We cannot hear you. Maybe you are muted.
Can you hear me now?
Yes.
Okay. So the question, your question is about the integration, if I have understood well.
Yeah, sorry, because they told me that I'm speaking too loud. Yeah, so how are you integrate these two cells, and what is the...
Okay, clear. So our artificial leaf is the result of the integration of a photovoltaic part with an electrochemical cell. So the operation of capping is not triggered at all because we need to match the two polarization curves, which depends in turn on the individual optimization of the two systems. So while for the electrochemical cell, we are strictly related to the operational conditions or the over potential needed to maximize the Faraday selectivity towards the desired product. For the PV cell, we are more flexible because we can choose the number of cells to introduce in the PV panel, so to obtain the desired cell voltage. So in Messina, we have some experience in this kind of operation. Sometimes the capping procedure is the result of a compromise among many different factors, performance, selectivity, and stability of the materials. So it's very important not to move far from the maximum operating point. That is the point where the PV panel has the maximum efficiency. So then regarding the Faraday efficiency, okay, it's difficult to answer now because of course it depends on the materials, on the behavior of the electrocatalytic behavior of the materials that we are developing on the project. As I said during my presentation, these reactions are very challenging, so there is no literature other references. Anyway, we expect to have values higher than 60% is our expectation.
Thank you, Claudio. Ambitious target. So for Silinda, and I would like to ask you, so you mentioned the oxalic acid. Why the oxalic acid? Why is this compound so important from your point of view?
Sorry, can you repeat?
Yes, can you hear me well?
Okay. Yes, because now I can hear.
Okay, sorry. So why oxalic acid is so important?
Oxalic acid is important because it's the first step, or better, the second step in going from CO2, because CO2 has one carbon atom, and it's normally chemistry. It's very difficult to make a carbon-carbon bond. Normally, the conditions are very strong, high temperature, high pressure, to make Fischer-Tropsch to form carbon-carbon bonds. So the step is to go from CO2, which is the zero value or product to formate formic acid, oxalic acid, and then from oxalic acid, it's possible to go to higher carbon, longer carbon bonds, to go then also to polymers.
Yes, thank you for your answer. This one is for Elis Hernandez. We have seen the pilot plans your project. It's really impressive. What have been the main challenges towards the scaling up of the electrochemical CO2 conversion units?
Can you listen to me?
Yes, we can listen to you.
Okay. Regarding the electrochemical units, as I said, we are building stacks of 0.1 meter square electrode size. And this is a challenge also in the field of CO2 electrochemical conversion, because I think it will be one of the first examples of this size of electrochemical stacks for this application. And the main challenge are related to the reproducibility of the activity of the catalyst in the high scale. For doing that, in Recode, we are our partner Avantium is focusing on the scaling up of the electrodes exploiting the catalyst that has been developed within the project by other partners, and they have I think proprietary technologies for scaling up these systems, but and they have also some patented catalysts for the production, for example, of formate. So based on the technologies that they are using for developing gas diffusion electrode system, they are able to maintain this stability also in the high scale. Another challenge is related to the not only to the scalability of the electrode, but also to the continuous selectivity and productivity over time, so the stability of the process itself, because as we know, the electrocatalysts under reductive conditions are subjected to degradation, but not only because the material detached from the electrode, but also because it could be reduced, chemically reduced, for example, in the case of copper-based catalysts. And also the regenerability of the electrodes during operation, so being able to tune operative conditions to maintain the stability of the process is another challenge that we are facing and that we are going to study and to investigate in the TRL6 demo campaign.
So our last question is for Julia and Horatio. First is, how does this project fit the implementation of the EU Green Deal to the production of sustainable fuels and chemicals? Which is the webinar name.
I think it's directed to both of us, but yeah, I can cover that while Horatio is coming. I think that it's very important to see that, as I said, we are focusing on developing different projects and different solutions. We are 15 PhD students and early stage researchers working with different systems and techniques to improve all the pathways for producing solar chemicals and solar fuels and changing the way the industry sees and uses these kind of chemicals. So I think that it's a very important thing, not only producing and changing the industry, but also the education part of our project that I think is our differential in this event today.
Yeah, that's important. I don't know, Horatio, would you like to add something to Julia's answer? Or...
Well, the only thing I can just, let's say, reinforce the second part, which is the importance of education. So well, we are not only producing like possible technologies, we are producing maybe people who will create future technologies. So I guess we're also a product, well, living one, but also a product, right?
Indeed, a very important product. Okay, thank you, Julia and Horatio. So this will be all regarding the questions, and so we don't have more time. So I would like to thank all of our audiences for attending today. I'd like to thank all the presenters for their time and presentations of their respective projects. We will be sending the materials to the attendees, and also the materials will be found in the SunCoChem webpage. Okay, so yeah, brilliant. So again, thank you very much for your attendance. I hope you had a good time with us, and have a nice day to everyone. Okay, bye bye.